the bottom, which is how to derive geometry from coordinates, or in this particular case now we're talking about components of vectors. So this is the magnitude of a vector found in this very easy way. And now the question becomes, what about the angles? I hope that example that I had, next page, suggests why angles are important. The example was of the stocks and bonds, and evaluating things in a abstract n-dimensional space, evaluating what things are going on. And in this particular case, the direction is kind of a right direction along this advice of keeping the particular ratio between the stocks and bonds, and then how far you deviate from it. That deviation is measured in the 90 degrees angle. Up until this moment, we don't know how to measure angles in dimensional space. This is two-dimensional space, but that's only two items that you have in your portfolio. If you have hundreds, then it will be 100-dimensional space. Okay, so we still need to figure out how to measure angles in that setting. So once again, this is 90-degree angle. Okay. And so if you're moving in a particular direction, you want to know if you're moving in what's the angle with the right direction. Okay, so we started looking at the angles between vectors in terms of the components, and the first look is one-dimensional, which suggests to what we're supposed to look at, and that is we have to look at the components of the vectors. But it doesn't really matter ultimately that the magnitude of the vector doesn't matter, only the directions that we are concerned with. So directions only. So let me have another picture here. This. Okay, so that's what I'm talking about. Directions. There is a point P. There is point Q, but the directions, if you only care about the directions, are either point in the same direction or in the opposite direction. Both of them are expressed in terms of the coordinates, components of the vectors, and to determine whether the direction is the same or not. It'll only take very little. You only have to compare the signs. So as you can see over there. So the components is 1.8 at the top left, coordinate is 1.8 and 3.5. What I do is I multiply them and look at the sign. So in this particular case, the sign is positive, so the direction is the same. That's the conclusion. Over here, the product of those two is negative, so they're opposite. So opposite coordinates, and they're from the origin, they're pointing in the opposite direction. So remember, once again, all the vectors start at the origin. So those point P and Q is really what we're talking about. We're talking about OP and OQ, two vectors, and we're looking at whether or not they have the same or opposite coordinates. So it's then positive, positive, same, negative, negative, also the same, and then if positive, negative, it's the opposite. Okay, so and once again, magnitude doesn't matter because we're looking only at the sign. So it turns out, as I started doing it here, it is about the angles. So let's speak of numbers. So x, how about, well, let's say A and B are two. I'll use the same letters for the components because it's just a number. Okay, so this is A, and then possibly this is B. Okay, so A times B positive. Then angle is 0. A times B negative. Angle is pi. Okay, so now it is a bit simpler than that. because as I chose here A and B unit vectors. Remember, unit vectors are the one with the magnitude equal to 1. So in other words, there are only two choices. A and B are 1 or negative 1. So then it is simpler. So A times B is 1, then angle, well, let's call it alpha. Alpha is equal to 0. A times B is equal to negative 1. Alpha is equal to pi. Okay? So once again, I simplified to the extreme. So we have only two vectors to compare. Unit vectors, which means that either they are both 1 or negative 1. Either one is 1 or negative 1. So when I multiply them, I will produce then either 1 or negative 1. So there are only two options, and it matches perfectly with our idea that it could be, the angle could be either 0 or it is pi. So once again, this is angle alpha is 0, and here alpha is pi. Okay, so this is the starting point. And at this point, now we'll see if you remember your trigonometry well. What is the relation between these numbers and those? What?
On the unit circle, 0 is on the right and pi is on the left.
So the angles are 0 and pi. Okay, so yes, it is about trigonometry. So how do we produce 1 and negative 1? What? It's cosine. It's cosine. Cosine of 0 is 1. Cosine of pi is negative 1. Right? So in case you don't remember, I plot that unit circle, and then I have only two options, either this. So this is 0, and the angle is I'm sorry, in the projection on the x-axis will be 1, right? So this is 1. Or it is, I'm on the other end here, and this is negative 1. So the angle is either 0 or pi, and that's what we've got. So it turns out that what we're after is the angle will be determined by the product of the coordinates to begin with, or components, and ultimately we're after cosine. Okay, so in fact I could state this explicitly if I want one formula. It's really uncomplicated now. So well actually I want to make it slightly harder, and that is, remember once again that this was very simple. And it was because I chose the vectors to be unit vectors. But generally speaking, they are not necessarily unit vectors, so which means that we're going to be looking at, you have to divide by its magnitude first. So I'm talking about then, instead of multiplying A times B, I will multiplying the corresponding unit vector. So let me maybe take a moment to mention that. I don't think we talked about that a lot. So if A is a vector, its direction is given by its normalization. Which is simply A divided by the magnitude of A. Well, A is not equal to 0. Okay? So that's the definition of a unit vector. What is the meaning of the direction of a vector? Well, magnitude doesn't matter, so how do we take magnitude out of consideration? We divide by it. So that when I divide it, A divided by A, magnitude of A is a unit vector, so, well, it's easy to verify that this is indeed a unit vector. I guess we didn't. I think I missed this. Yeah, there's an important property here, so I think I missed it. So, well, let me take a moment to go back and fix that. So it is a unit vector. that this is a unit vector. You can see what I did here, and that is I factored this out. So the relation between, I don't know how I overlooked it, the relation between the vector, okay, now I see why I missed it. The relation between the magnitude of a vector and its and algebraic operations. We and I can't find it. And algebraic operations. So remember, where it's here somewhere. The triangle inequality, all their related business. The triangle inequality, no. Oh, here it is. Okay, so that wasn't a long time ago. So it was just last time. The properties of magnitudes are on the right, but this is not a complete property. It is. I'm overlooking a more important case. I went straight from the property of the distance, and then I ended up with this property of the magnitude. But there is a stronger condition here, a stronger property, and this is what happens under scalar multiplication, because none of these properties actually is about scalar multiplication, but rather this is a x. So if I multiply x by a is a number. What happens to the magnitude of the magnitude of x? A times. Careful. A times? Almost. So this is what we're trying to say is this. There is something missing. So yes, so we stretched or shrunk vector x by a factor of a, and then it is quite clear what's happening to the magnitude. It is increased or decreased proportionally by that number. There's a little problem here about a. It could be 0. It still works out, right? So you multiply a vector by 0, and then you have a 0 vector, and its magnitude is 0. So you multiply by 0. When a is 0, it works out, right?
Can it be negative?
That is the question. Can a be negative?
Probably not.
Well, it could be. Hypothetically, we can multiply by a negative number. So how do we fix the formula? Absolute value, right? Okay, so and then you can see that the original property is included. Right, so if I just say a is equal to -1, I have my property on the left, right? Because its magnitude is equal to 1. And so there is no difference going left or right produces the same effects. Yeah, so sorry about that. I overlooked this more important property. So every time we have two algebraic operations on vectors, and now we established a relation between those two and the magnitude. Okay, so and that is the property, that is the new version of the property that I just used at the bottom here when I was talking about verifying that normalizing the vector gives you a unit vector. Okay, so that's normalization. Well, it's called normalization because that of the other word for magnitude, that is the norm. So you make the norm equal to 1. That's normalization, sort of. So if you have vectors of unknown length, other than 0, then you can make it into a unit vector by rescaling appropriately. So that's uncomplicated, hopefully. But then what we can do is then we take this idea to what we see over there, and we are realizing that we're not multiplying a and b, but rather we are multiplying their normalizations. So which is what I mean is, if we look at the table up there, that's what I'm talking about. The angle doesn't change, right? So we only care about the direction. So replacing a with its magnitude is the same. So like this. Replacing it with its normalization still gives me the same direction. So alpha is equal to 0, and then the same product is If the same product gives me -1, then the angle is pi. So once again, that you could call it. So that's just a restatement. The theorem itself, you want to have one formula, rather than if-then. Two cases, you can put it in a formula, and then this is how you just use our cosine. So alpha, well, I don't want to use our cosine. Let's just say cosine. So cosine of alpha is A times B divided by magnitude of A times magnitude of B. So once again, it is expressed in terms of the components of these two vectors. They could be arbitrary. Okay, so but the main idea is, of course, it's about multiplication of the components. So now, so that's dimension one. What happens to dimension 2? I may have a picture here. So this is what we're after. Two vectors, OQ, OP, or rather OP, OQ, the angle that we want to find about it. The coordinates I indicated there with those blue dots, the four numbers that we all have available, other than two numbers that we just used in one dimension. We have now 2 and 2, 4, and that the angle beta over there. That is the angle. I'm sorry. We have two angles, alpha and beta, that are the angles with all the two vectors with the x-axis, right? You see those two arcs, and then the angle that we care about is the difference. So this is the angle that we care about is this. So the angle between the two vectors. Okay. So we could find those two angles. We can find alpha and beta. I already found them over here on the right. It is nothing but, what is it? Cosine of these two angles. It is, oh, look at the coordinates. It is the it's y. It's the value of y divided. So it's the y coordinate divided by the hypotenuse, right? Y coordinate and the numerator and the. So it's the definition of cosine pretty much. Except it is the definition of cosine, except it's I allow y to be negative. If we work out if y is negative as well. Okay, so and then so then you can see the plan is I can find cosine. I could also find the sines. In fact, I would need both the sines of these two in order to produce what I'm after. I am after the that angle over there, the yellow angle. Fortunately, there's a formula that expresses cosine of the difference of two angles, right? So the angle that I'm after, let's say gamma, gamma is equal to beta minus alpha, right? Beta minus alpha. So fortunately, if I know sine and cosine of angles alpha and beta, I can express the cosine in terms of those four. So that's how it works out. I'm not going to go into detail, so I'll just supply you with the answer. If I can just find it. I'm not in the right place. Just a minute. Scrolling. Well, the formula is actually we can guess what that formula is. Maybe let's instead guess what the formula is. It's actually easier than going to all the trigonometry. It is easy to guess what the answer is. We just keep in mind what the operation is in dimension 1, and then see what we should have in dimension 2. So in dimension 1, we multiply the coordinates, so we're going to probably multiply the coordinates components in dimension 2 as well. So the idea is, well, first of all, this remains. I could still have these vectors, and once again, that remains the same. So this is, well, let me just write out. Well, what you're looking at is the angle between, what is it, 1, 0 and negative 1, 0 is pi, right? On the other hand, if I go now vertical like this, so then what do I say? The angle between 0, 1 and 0, negative 1 is pi, right? So once again, this one also pi. So do you see what's happening here? We're looking at the one coordinate at a time. So either in the first example here, I will have to be looking on the x coordinates, and I multiply 1 times negative 1 to find just the way we established in dimension 1. In the second example, it's the same story. I multiply 1 by negative 1 to find to get negative 1, which means that the cosine, the angle is pi. Okay, so it is the question that's easy, right? That's simply the dimension 1 repeated for x-axis and y-axis separately. And the real question is what if we have a mixture? And by the mixture, I mean what if we rotate through pi over 2. So what I'm talking about is these. So number 3, angle between 1, 0 and 0, 1 is pi over 2. Okay, so, well, since we know that's about cosine, what's cosine pi over 2? Zero. What is that? Point I'm trying to make here. Still a bit. Scrolling. Okay, so the question is, how do we get 0? So 1 times negative 1 gives me negative 1. That's the cosine of pi. Same story is here, right? But this time we got 0. How do I get the 0 from these?
1 minus 1?
Almost. No, there is no minus.
X minus y then?
No.
Well, it's like 0, okay, well, like 0 times 1 times 0 gives you a 0.
That's right. We're keeping x's with x's, y's with y's. So it will be, I have 1, 0 on one hand, I have 0, 1 on the other. So what if I multiply 1 times 0 and 0 times 1 and then add together? That's how I get a 0. Okay, so at least that's the idea of how we're gonna handle it. We're still doing the same thing as one dimension. So we do one coordinate at a time and we multiply the coordinates. So that's exactly what I did, right? 1 times 0, 0 times 1, and then we add. That is the last step that takes some effort. So okay, so that is let's do one more example to confirm. And I want. How about I take this one. Well, let's just take 1, 1 and 1, 1 and negative 1, 1. Right? So if I carry out the same operation, negative 1, 1, 1, negative 1, what do I get? Negative 1 times 1 plus, hold on a second, 1, 1, 1, 1, well, I have an extra minus, I'm sorry, right here. I don't need a minus here. So 1 times 1, 1 times 1 plus 1 times negative 1 is 0 again. Okay, so once again it works out. So this is called the dot product. The dot product of two vectors. So dot is not to be overlooked or omitted. It is important. So I still maintain that there are no multiplication of vectors. So when you hear product, you might think this is multiplication, but no. And the main reason is what is the nature of the dot product? It's a number. So vectors, say AB dot CD is AC plus BD. Okay? So once again, component-wise multiplication followed by addition. So it is not a vector. So when you want to say that you multiply vectors, there's an implication that you're producing another vector, and this is not a vector. And it couldn't be a vector because think about, we're talking about cosine. So the number that we're producing is not literally, but it is the cosine of a certain number. Okay, it gives us the angle. Okay, so well, let's do it one more time. I want to have just to convince you that indeed that everything works out. How about this one? Well, okay. So how about 1, 0, and this one, 1, 1. Okay, so I take the dot product. So 1, 0 dot 1, 1 is equal to 1. So what does it look like? So this is supposed to produce the cosine, remember, of the angle. What's the angle and what's its cosine? So if this is alpha, what's cosine alpha? Or, well, the angle is what? Pi over 2, pi over 4, right? So alpha is pi over 4. What's cosine of pi over 4?
1/2.
No. 45 degrees? Square root of 2 over 2. That's right. Okay, so we have a mismatch. Why is that?
Is it sine?
No. We forgot to do something. So mismatch. Well, when it is 1, you know, for the cosine to be equal to 1, the angle would have to be pi. And this is definitely not pi. So what did I forget to do? I forgot to normalize. So I have to multiply the vector, the two vectors, not the two vectors, but I have to multiply, do dot product of their normalizations. So in other words, it only works when you're talking about unit vectors. The first one is a unit vector, but the second one is not. What's the length of this vector? 1 squared plus 1 squared squared, it is square root of 2. Okay, so in order to thing to work out, I have to divide by square root of 2. So 1 has to be divided by square root of 2, and then the whole thing then becomes 1 over square root of 2, which is the same as 2 over square root of 2. So then it does work out. Okay. It was surprising that it did work out here, but since it's 0, it doesn't matter whether you normalize or not. If you end up with 0, it is always the case that you're going to, or either vice versa. If the two vectors are perpendicular, it doesn't matter whether or not they are normalized, the dot product will produce 0. Yeah?
Shouldn't be square root of 2 over 2 the final answer?
It's the same thing. Square root of 2 over 2. Oh, I'm sorry.
Right.
Yeah, no, wait a minute. Hold on a second. What did I... where did I mess it up? 1 over square root of 2. What is... I ended up upside down. 2 over square root of 2, not square root of 2 over 2. Okay, so yeah, so I guess my explanation wasn't quite right. No, hold on a second. It's supposed to. Okay, let's find a mistake here. What?
When you multiply it by square root of 2, the answer would be square root of 2 on the top and 2 on the bottom.
At the very end?
Yes.
1 over square root of 2, yeah, okay, thank you. I was afraid that thank you. So it is indeed square root of 2 over 2. Okay, so we're good. All right. Okay, so it does work out. We had plenty of examples. Let me state that I stated a minute ago that A perpendicular to B when A dot B is equal to 0. Okay, so then that's when you don't have to normalize. Okay, so that's one important observation. In fact, it works both ways. So not just if, but if and only if. So let me make that clear. If and only if. Okay, so the dot product is 0 whenever they're perpendicular, and they are perpendicular whenever the dot product is 0. So that's a quick way to determine 90 degrees, and remember 90 degrees is very important to us with the Cartesian system that is the base of everything here. Okay, and then another important thing is to observe the meaning of the the meaning of the what if we dot product of a vector with itself. So what is A dot A? Or I put vectors here. Yeah, I forgot about that. My commitment to use the capitals for the vectors as well as points. So these are vectors. Okay. So this is, yeah. Okay. So what is the meaning A dot A? Okay. So if A is equal to AB, then what? A B, so A dot A is AB dot AB is equal to A squared plus B squared. So what's the conclusion? A squared plus B squared. The The vector is AB. So what's the meaning of A squared plus B squared? It is the square of the length of the vector. So you can put it in a theorem. One more theorem is that A dot A is square of the magnitude. So there is a relation, and in fact, an interesting thing that in fact we were trying to solve the problem for angles, but turns out that our solution also solves the problem of distances. So the dot product information contains all the information about distances, not only about the angles. Okay, so we don't really we can always get the magnitude back if we have the dot product, but not necessarily vice versa. Okay, so and then we just treat this as a definition. We treat it as a definition. We certainly explain it the idea of the angle computed through this dot product formula. We explain for dimension 1, dimension 2, it works out perfectly. And now dimension 3, you can do the same. It's just more complicated to begin with, but most important is that you are you don't have to. You suppose you have two vectors, and then are they in dimension 2, dimension 3, or higher? You don't know. It could be the whole space could be n-dimensional, but since the two vectors only determine a plane, then everything is still applicable in the exact same way as we do. So we don't really have to have the definition. We don't have to justify that the angle produced by the dot product is in fact we cannot justify that it is truly the angle. Best we can say is that this is how we compute the angle, and that angle matches the one computed if we limit ourselves to the plane determined by those two vectors. Okay, so this is vector A, vector B, and then even though everything lies in n-dimensional space, this is only dimension 2, and in dimension 2 we are in the position to do any kind of geometry, the geometry we just did, and then we'll just have to take it on faith that there is nothing bad happens. So even though the plane might be skewed, the computation of the dot product remains the same. It is the computation of the dot product is independent of the choice of the coordinate system, which is, if you think about it, it makes sense. So whether you have, well, I'm not sure if it is quite clear if the dot product between these two coordinate system, Cartesian systems, and we switch from one to the other, they will produce two different components for our vectors, right? So I have the same vector like this. They will have this vector will have different components, right? Because different system. However, in all the vectors, the same thing happens to all the vectors. Now the question is, will the dot product change? Well, an easy question is, will the magnitude change? It's the same vector. We have a piece of paper with a vector drawn on it, and then we put on top of it, we can put a Cartesian system. We do not change the vector. It's still the same vector, so it will have the same magnitude. If you have two vectors, once again, we put coordinate system on top of it, the angle doesn't change. So both the magnitude and the angle between two vectors will be the same no matter what the coordinate system is chosen. So that's why the whole thing works, even though certainly it requires proof, but we'll just take it on faith that things work out. So as I said, the coordinate system, the choice of coordinate system, as long as the origin is the same, the origin remains the same, it will produce the same geometry of the system with the same coordinates, with a different coordinate system. Okay. So so what I was saying then is the definition of the dot product and then the angle. So the definition So suppose A is equal to A1, AN, B is equal to B1, BN, are two vectors in Rn, then the dot product of A and B is the number A dot B is A1 B1 plus A2 B2 AN BN. Okay, so you can certainly see that the magnitude would definitely come from this. If I replace B with A, I will have the square of the magnitude, so that theorem at the top will remain valid. So let me jump to the angle. So once again, with the same setting, let me just continue with this definition. So I'll just say the angle between A and B. Now this time I require A and B not equal to 0. Is the number, say, alpha, that satisfies that equation that we had. So cosine of alpha is equal to A dot B divided by the product of their magnitudes. So in the denominator you see another dot, by the way. So the dot product is called dot product because we have to repeat the dot every time. Okay, certainly that explainable, but there is another dot at the denominator, but it's not the same dot. It's just a multiplication, yes.
What's the word after angle for A? Angle A.
The angle between A and B, okay. So it's a number alpha or angle alpha. You can in trigonometry you are allowed to have functions with angle that run between negative infinity and infinity. For cosine, and this time we certainly require alpha between 0 and pi, 2 pi. Okay, so as I said, the dot that we commonly omit when we multiply numbers, so I put it there just to separate the two magnitudes. Otherwise I have 4 bars in a row, so I have to separate them. I put the dot there, but that's not the same dot. That dot is the regular multiplication that we have been doing forever, right? So, but the one at the top, that is the dot product dot. Okay, so so we'll get to the properties. I hope multiplication once again. So let me once again put this in front of you. How you do dot product of in the column notation. So, going component-wise, we do not mix coordinates, ever. I don't believe, not in this course. So 1 times 0 plus 2 times negative 1 plus 0 times 2 plus 1 times 3. Okay? So 0 minus 2 plus 0 plus 3. Okay, so 4-dimensional, 5-dimensional, doesn't matter. That's what we're doing. We have our dot product. And I didn't, but certainly when you have 1, it does not give you the angle. So carefully look at the formula right above. You have to normalize and divide by the magnitude of or the product of the magnitudes of the two vectors in order to get the cosine. Otherwise, what you're getting is unclear. For 1, remember, by the way, this is probably important to connect the two. Remember that cosine, what do we know about cosine? Let me take that formula. So this is the most important formula here, so both of them. So what do we know about cosine? As a function, or the value. What kind of number is it? Between negative 1 and 1. That's right. So cosine alpha lies between negative 1 and 1 indeed. So which means that that number over there will have to lie between negative 1 and 1. And that is why we have to normalize, otherwise it's not going to work. So if you can take dot product and with two vectors, and you can get any number you like. I got 1 over there. There was a pure coincidence, right? I could have gotten 100. So if you do not divide by the product of the magnitudes, okay, then you might get a large number. So it cannot be cosine of anything. Okay, so just a way to remember why it is so important. But also, I guess we are seeing here. This is what we're seeing here. So, so what the conclusion is, this is how you can write the conclusion here about the dot product. A dot B absolute value is less than or equal to the magnitude of A magnitude of B. Okay, so it is. I am doing it a little bit backwards, not entirely backwards. You should start with this inequality that I have here, which would justify then, if I go backwards like this, it would justify that to call this expression over here cosine. So you have to know that that fraction is less between negative 1 and 1 in the first place in order to require that, not to require, but claim that actually there is some angle alpha between 0 and pi, so that cosine alpha is equal to that expression. So if you want to be strictly logical, you have to go backwards. You have to justify that inequality at the bottom with algebra. Okay, not too complicated, and then you will know that your definition of the angle makes sense. Otherwise, it might not be an angle. If all we know, it might be that expression might be equal to 100, and so there is no angle for it. So fortunately, if we have time, we'll look into this next time.